Alright, so this is our last concept for this unit. We're going to be talking about binomial distribution. So we've talked about binomial distribution in like 3 lectures ago. We're going to see how it is actually used in probability. It actually makes a lot of problems very quick and easy using this method. So I want to start off by showing you why this makes sense, because this is our only concept, so I can actually use these 30 minutes. So let's assume that we are rolling a fair dice 4 times, and we want to find the probability that we roll. So we have 4 dice, and we are trying to find the probability that we roll all 3s. So every single one of these, we want it to be a 3. So we can think about this as doing separate probabilities and using that multiplicative property of probability. So for my first dice, if I want it to be a 3, well, there's 6 sides and only one of them is 3, so that's a 1 out of 6 chance. Same for the next dice, that's 1 out of 6 chance, 1 out of 6 chance, 1 out of 6 chance. So we can multiply all of these together and we get the probability that all 3 of these is going to be 0.0007. So the probability that all of them become a 3 is 0.0007. Not a very good chance of that happening. So then let's think about the other one. So where none are 3s. So not a single one is going to be a 3. So we can think about that by doing the same thing, where we have 4 dice and we want to check out their probabilities. So the first one, we don't want it to be a 3, and since only one of them is a 3, that means that I have 5 other options that are good, that are not a 3, out of the 6, and that would continue for every single one of these. So we can multiply all these together and get that out. That is going to be 0.482225, etc., etc. So almost a 50% chance that none of them are going to be a 3. Okay, so these are the pieces of math we've already done. So now, what though if I ask for exactly 2 3s? So I want exactly 2 of these dice to be a 3, and the other ones I don't want it to be a 3. So we can start by thinking about that. So we can start here, and the first one we want it to be a 3, so there's a 1 out of 6 chance. For the next one we also want it to be a 3, that's a 1 out of 6 chance. The next one we don't want it to be a 3, so that's a 5 out of 6. This one's also a 5 out of 6 chance. So the thing with this though, that's not the only way that we could get exactly 2 3s. Because this is the first dice, the second dice, the third, the fourth, so forth and so on. So that means that these could be located anywhere. This 1 6 could actually be over here for this dice, or this dice, or so forth and so on. So we actually have a combination of ways happening where these 1 6 could be anywhere. We just want these 1 6 to be somewhere in these 4 spots. Combination. So this is actually a combination where out of the 4, we want it to only choose 2 of them. So out of the 4, we want 2 of them to be the 1 6. We don't care what it is. So we can actually go and multiply all these, but one nice thing is that this 1 6 times this 1 6 is really just 1 6 squared, and this 5 6 is also just 5 6 squared. Here's that piece of that binomial distribution that we talked about a couple videos ago, where this is really something like we have 1/6 plus 5/6 raised to the 4th power, and I'm looking for the term where the 1/6 is squared or something like that. It's the exact same concept. Here's my A, here's my B, and here's my n value that I'm raising it to. So I can find the different terms using this. So we can go and plug in our combination times each of these pieces and get out what the probability is. Because again, the exactly 2 means that the 2 could come from any of these 4 dice. It's not just the first 2. It could be the 1st and the 3rd, or the 1st and the 4th, or the 2nd and the 3rd, or the 2nd and the 4th, or the 3rd and the 4th. I just listed out all the different ways. So, 4 choose 2 is 6, so there are 6 ways that I could order, or not, 6 ways that I can go and combine these with these 1/6 being in different locations. I don't care that which 1/6 is which. I just care that they are in the different spots. So this is going to be, let's do this math. So we got 6 times our 1/6 squared times our 5/6 squared, and we get out 0.1157. So pretty close to 1/8 of the time we will get out exactly 2 3s. So nothing else. We don't care about what the other 2 came. We care that it was exactly 2 3s. So we can kind of think about this as 1/8 of the time we should see a pair pop up, and no more than that pair, which is kind of an interesting idea. If you were rolling 4 dice, 1 out of 8 times you should see exactly 2 of some number. It doesn't matter, this could have been a 4 or 5, so forth and so on. So here is our math that we're going to be doing today. So the idea behind this binomial distribution probability is that we want to think about things in being successful and being a failure. So we're going to be thinking about things being successful and things being a failure. So the probability of a success and the probability of a failure. So because those 2 things, it's either a yes or a no, we did it or we didn't do it, those 2 probabilities should add up to be 1, because that would be 100% of all of our sample space. It either happened or it didn't happen. So the let's see. So I'm going to write out what all of these terms are going to be. So the probability of something to be successful is going to be P. So the probability of something to fail is going to be our Q. So our N is going to represent the number of success. Oops. And our R value is going to equal the number of failure. So a couple things with these letters. So P is going to, or I should say P plus Q is going to equal 1. So these 2 probabilities should add up to be 1. So that means if you know the probability for success, that just means Q is going to equal 1 minus whatever your P value was, or vice versa. So also, N plus R is going to give you your total number of chances that you were taking. So I shouldn't say it that way. I should say it as n is really the that's fine to say it this way. So our formula is going to be n choose r, where n is really your total number of cases, and you're trying to choose, I should really write it that way. So n minus r is going to give you your number of failures. That's better. So n choose r, so our total number of chances that we want, and we're trying to choose how many successes we want to happen. And we're going to multiply that by the probability of success raised to whatever our r value is. So saying that I want 2 successes times our failure rate raised to the n minus r, which was our failure rate. So a better way to view this is going to be the total cases. So total cases, choose how many successes you want, times that probability for success raised to the number of successes you want, times your failure probability times the number of failures you want. So these problems right here will help us when you see words like exactly or at least or at most, something where you're trying to limit your sample space to be a precise number. So an example of that would be that Michael makes 90% of his free throws if he shoots 20 free throws, and if his chance of making each one is independent of the other ones, basically so it being independent means that if he makes one, it doesn't matter that he just made that one. This next one is totally independent. It didn't matter that he made that next one. So like he doesn't feel the pressure that he missed, so he has to make it kind of concept. We want to find the probability that he makes all 20 of them. So what is the probability that he makes all 20 of them? Well, this one's pretty straightforward, but we're going to use this binomial distribution just to kind of make it go a little bit quicker. So it says that he makes 90% of the free throws, which means his probability of success is going to be 0.9. So that means that his probability for failure is going to be 0.1. So 1 minus 0.9 was 0.1. We want to see if he makes a total. So there were a total of 20 shots. We want to see him make all 20. So him making all 20, that would be 20 choose 20. So the total number by how many successes he wants, we want to make all 20 of them, times the probability of success, which was 0.9, raised to how many he wants to make, which was all 20, times his failure, which was 0.1, times how many failures? Well, that's none. So a couple things with this right here is that this is 1, and this is also 1. 20 choose 20, there's only one way to choose all 20 of them. And anything raised to the 0 is also 1. So if you want to make all 20, or make every single one of everything, it's just going to be your success rate raised to whatever the total was. So we can see what this comes out to be. So basically also an eighth. So this comes out to be 0.1216. So basically for him to make all 20 of these free throws, there's only basically a 1 in 8 chance of that happening. Which is kind of low, but he had a 90% chance. But you have to think, there's also him failing here 10% of the time. So there is still a large chance for him to not make one of those. Okay? So another example, we want to make exactly 18. So exactly 18. So using all of this information still, that means that of the 20, we want to make only 18 of them. So 20 choose 18. So this is your 20 choose 18. It's the same exact format, just me not writing it in this notation. So this would be 0.9 raised to the 18 times 0.1 raised to the, well, if he makes 18, that means he has to miss 2 of those 20. So we can plug that in. Ooh. And we get 0.2798. So roughly 30% of the time he will miss exactly 2 of them, or make exactly 18. So it doesn't matter which ones. He could have missed the first one and then missed the last one. He could have missed the last 2. He could have missed 2 in the middle. He could have missed number 5 and number 12, so forth and so on. It just means, so we've looked at every single one of these different combinations to make exactly 18. So that means he made 18 and failed twice. All right. So at least 18. So now I'm going to remove this board. Actually, I'm going to keep this board. So the last one says at least 18. So at least 18 means he made 18 or more, because 18 is the least number possible. So that means he needs to make 18 or 19 or 20. So if you remember with probability, this or means that you add your probabilities together. So that means we just need the probability for 18, which we already found, the probability for 19, which we haven't found yet, and the probability for 20, which we already found. Add them all together, and that gives us the probability of making at least 18. So we just need to find the probability for 19, because we already have 20 and 18 in this example. So let's find out 19. So for 19, that would be 20 choose 19 times 0.9 raised to the 19th times 0.1 raised to the 1. Plug that into our calculator. And I get 0.2702. So I'm going to add up all of these numbers to be able to answer this at least. So I've rounded. So again, if you can not round until the very final answer, that would be better. But this gives me 0.6716. So here, this larger number makes more sense to this 90%. because we're now seeing him making all of these different combinations of things happening. So that means this, so basically almost 70% of the time he's making at least 18. So he made 18, maybe 19, maybe 20, but he made at least 18. So about 70% of the time he could make at least 18 out of his 20 shots, with his success rate of being 90%. So this is why this binomial distribution, that why I talked to you about it in the beginning, it's because of probability examples like this, and why this makes it go so much quicker instead of actually having to try to figure out the different ways. So at this point, you can now complete the homework from that probability sheet. So you can now do 6 through 25. A couple of announcements before I go, so you can start writing your questions now and I will answer them. But a couple of announcements. So we have our test on Friday, so that's when your homework will be due for that. There are, let's see, it's loading, so I will tell you how many different homeworks there were. Let's see, 1, 2, 3, 4 different homework assignments that you will be turning in. So there's the binomial distribution homework, there's the probability homework that you can now do all 25 of those problems, there's the conditional probability, and the expected value homework. So there's 4 things that you're going to be turning in to me on Friday. There's also a review guide up there. Again, I'll do the exact same thing I did with the last review guide. I will take it as 30 points extra credit on homework, which is huge to help increase any grades, get them exactly where you want them before the end of the semester. So just so you know, this is the last unit for regular pre-cal kids. So accelerated, we still have one more that we're going to try to go through as quickly as possible. There may or may not be a test on that. I'm not sure. It's over some statistics material. So I'm going to try to figure out how we're going to do that, since coming next week we only have only 3 days I can actually give you new material on, so we're figure that out. There's a video project that I posted up on the class notes page, so take a look at that. I'm going to be sending out a remind, letting you guys know about that, so start thinking about it. You can work in a group of up to 3. You can also work alone if you want to. Just start looking at that, or answer any kind of questions through Remind and whatnot. So do any of you have any questions? Let's see, Kennedy, for exactly this one you got 2.51. Same. Aaron, did I? Oh, I see. Yeah, hold on. I see. I did it in my calculator wrong again. Yes, that was 2.852. So then that would have messed with this number slightly. .6770. Sorry, I had been using the answer button, and my previous answer was not exactly what I wanted it to be. So, yes, that was right, Kennedy. it's another, so the video project is just going to be another thing. I'm going to take it as both a quiz and a test grade to kind of but we won't have a final in this class. I don't even want to think about how I would try to proctor a final. Regular pre-cal kids, it's basically you have a test on Friday and then you have this video project. Same with seniors, because you fall into that category. My accelerated, we'll probably have like a couple more lectures, but for the most part you also have this video project as well that you're going to be working on. It will just be like your own kind of time going on. Wednesday during our normal lecture, I will be doing a review period, so that 9:30 till maybe a little bit before 10:30, since my wife has a meeting. Or do another Zoom call so you guys can ask any kind of questions then. Also Thursday, or also hold on to that 5 o'clock slot. That way you can ask questions as well then. Yes. So, any other questions? Alright, so again, look at my website for that video project information, or send out a remind. Start thinking about who you want to work with, or seniors, look at what you're asked to do. Otherwise, let me know if you have any questions over the homework.